This is part 2 of Chapter 16's lecture outline. All right, we're going to continue on Chapter 16 with atmospheric heating. One thing to keep in mind when we talk about energy transfer in terms of heat is that heat is always transferred from a warmer to cooler objects. Now, there's different mechanisms for transferring heat, and there's three important ones that we're going to have to worry about. And this next picture describes the three rather well. The first one we're going to talk about is conduction. So in this picture, there's a metal pot, and presumably the handle is also made out of metal. So as the pot heats, the molecules in that pot are also going to start heating up and go from the cooler side, which would initially be the pot, and then it's going to move upwards through the handle. So eventually your hand would feel rather warm as you hold the pot. That would be conduction, when heat is transferred between molecules. You also have something called convection. So when this water boils, you have a circulation of molecules within that substance. So you have hotter molecules moving upwards towards the cooler molecules, and then there has to be a natural cycle backwards down. So that's typical of convection. And then the third type is radiation. So hotter objects will emit electromagnetic radiation, and specifically infrared waves. So these red squiggly arrows are representing infrared waves being emitted from the hot fire. So they're the three methods to transmit heat energy. So we already talked about radiation in a previous chapter, and we know they consist of electromagnetic radiation consists of different wavelengths. We've talked about these already. And we've also already talked about the electromagnetic spectrum, where the visible spectrum only makes up a very small portion of the overall electromagnetic possible wavelengths. Now, radiation, there are some special laws dictating what type of radiation is emitted from what objects. So all objects, regardless of temperature, as long as it's not at 0 degrees Kelvin, will emit some radiation. So hotter objects radiate more total energy per unit area than cooler objects. And the hotter the radiating body, the shorter the wavelength of maximum radiation. So objects that are good absorbers of radiation are also going to be good emitters as well. So metals tend to be good absorbers of radiation, but then when they're heated, they're also good emitters. So let's talk about incoming solar radiation. So our atmosphere is largely transparent to incoming solar radiation, meaning that much of the visible light actually makes it down to the Earth's surface. There are some atmospheric effects that you should be aware of. We have reflection, scattering, and absorption. Absorption is pretty self-explanatory. That's the incoming radiation being absorbed by the molecules in the air. We have scattering. So when incoming solar radiation will actually bounce off molecules and scatter off and reflect in different directions. And then we have straight reflection, which is, depending on the color of the thing that light is being shown onto, a certain percentage of that electromagnetic radiation will be reflected. And we refer to the amount of energy that's reflected as the albedo. So about 50% of the incoming solar radiation is absorbed at Earth's surface. So this is just some examples. So we have, if so all of the radiation was coming from the sun, about 5% would be scattered back into the atmosphere. Some is lost to reflection and scattering out into space. A large percentage is reflected off of clouds. A large percentage is also absorbed by clouds, and about, like I said before on the previous slide, 50% actually reaches the surface of the Earth. So this is an example picture of showing you different albedo. So as an example, grass reflects about 5 to 25% of the incoming radiation, where something like a light-colored roof is going to reflect 35 to 50%, or a darker roof will only reflect 10 to 15%. So in this diagram, the house with the black roof will be a lot warmer than the house with the lighter roof, because if you remember, the color black is basically showing that not much is being reflected. A lot of the energy is being absorbed by that color. So if you're ever going to put a roof on your house, make sure it's not a super dark color. Otherwise, a lot of that solar radiation will be absorbed. So Earth re-radiates some radiation when it does accept that radiation from the sun, but it does so at longer wavelengths. So what this means is that longer wavelength terrestrial radiation is absorbed by carbon dioxide and water vapor. So if we have large concentrations of carbon dioxide and water vapor in the atmosphere is going to heat up, and the heating of the atmosphere is termed the greenhouse effect. You've probably heard that before. So essentially how this works is the solar radiation comes in and it hits the Earth's surface, and then some of it is re-emitted by the Earth, but at much longer wavelengths. So if there are a lot of different things in the atmosphere that could absorb this re-emitted radiation, then the atmosphere is going to heat up a lot quicker. So that's why we try not to put too much carbon dioxide or too many chlorofluorocarbons into the atmosphere, because if we keep adding things to the atmosphere that absorb energy, eventually our mean temperatures are going to increase to the point where maybe vegetation can't survive, or it just becomes too hot to have sustainable life on the planet. So that's why the greenhouse effect is important. So let's talk about temperature measurements. So at any location, there's a daily maximum and minimum, and we also worry about daily mean temperatures, the range of temperatures on any specific day, the monthly mean, which is just the average monthly temperature, the annual average temperature, and the annual temperature range. One important thing when you're looking at weather maps, and you're going to see that in the next few chapters, there's going to be many maps to look at and analyze. One thing that you might see on a weather report is a map that has something called isotherms. And these are just lines on the map connecting points of equal temperature. So it's used to show the distribution of air temperature at certain locations on the planet, and also how the temperature is changing per distance. And we call this amount of temperature change per unit distance the temperature gradient. So in this example on the right hand side, it's not as good as the color one on the bottom, all these black lines represent areas of equal temperature. So since Philadelphia is in between the 60 isotherm line and the 70 isotherm line, the temperature in Philadelphia is going to be somewhere between 60 and 70, and they have it marked as 64. So all these black lines just represent areas of equal temperature. And this color version down here is a little better to look at. This is typically what you would see on a weather report to let you know what the temperature would be like in your specific region. Now, there is a big difference between the temperature at a location depending on if you're on land or near water or right on top of the water. So land heats more rapidly and to higher temperatures than water ever could. That's because water has something called a high specific heat. And the specific heat is the amount of energy needed to raise that substance by 1 degree Celsius. So since water has a really high specific heat, it takes a lot of energy to raise the temperature up just even 1 degree compared to, let's say, somewhere on land. The next few slides are just giving you some example differences between different locations at different locations on the Earth. So this is an example showing Vancouver and Winnipeg in Canada and the temperature differences where Vancouver is a marine location near water and Vancouver is in a continental region. So you have different variations in temperature over a monthly period. This is showing you that at higher altitudes you should have lower temperatures. So in this picture, La Paz is in a mountainous range, so it has a much lower temperature than Concepcion, which seems to be in a lower altitude region. This is just another example of a coastal city on the west coast versus a coastal city on the east coast, and how they can have different temperature ranges over a 1 year period. And this is an example of cloud cover versus some place having a high albedo. So if clouds have a high albedo, then clouds can cool air during the day, but it can also keep it heated at night. So just an example of how temperatures can change depending on if you have a cloudy day or a clear day. All right, so how do you measure temperature? This is the last topic of chapter 16. So the human perception of temperature, this is anything that influences the rate of heat loss from the body. And this also influences the sensation of temperature. Some important factors would be air temperature itself, relative humidity, so the amount of moisture in the air, the wind speed, and also the amount of sunshine. Now, world distribution of temperature, so when you look at temperature maps, remember they're typically going to give you an isotherm or isotherms, which again is just a line connecting places of equal temperature. And temperatures are adjusted to sea level. January and July are used for analysis because they represent temperature extremes. January is typically your most wintry month, and July would be a typical summer month. So there are some global temperature patterns. So in the southern hemisphere, isotherms seem to be straighter and they're more stable. And isotherms also show ocean currents. They're typically good predictors of ocean currents. So annual temperature ranges, so they're smallest near the equator. They increase with an increase in altitude, so the farther away you get from the equator, the bigger temperature range. And they're greatest over continental locations. So this is the world mean sea level temperature in January. So you're going to see down in the southern hemisphere, the isotherms are more straight. And they get kind of funkier as you go in the northern hemisphere. That's because most of the land masses are in the northern hemisphere of the Earth. And this is the world mean sea level temperatures in July. So obviously a lot warmer, but you'll still notice that the southern hemisphere isotherms are much straighter because they're lacking an uneven distribution of temperatures because of land masses. And that's all of chapter 16.